In the video called Discovering the Derivative of x cubed by Considering a Cube, we in fact learned that the derivative of x cubed is 3x squared. We did that by a geometric means that you won't see most places, but I want to show you here is the standard proof by which people usually show the derivative of x cubed is 3x squared. And more importantly, I want to show you how that standard proof, although it looks like a bunch of algebra, actually relates very closely, or actually exactly, to the geometric proof that we did in another video. So, how do we show that the derivative of something is something? We look at the definition of the derivative. Now, you need to become very familiar with this definition. I know it looks like a lot of scary symbols, stuff like that, but it's really very simple. If you keep in mind the strategy that we've used several times for finding the derivative as the instantaneous rate of change, the basic idea is contained in the last step here, that we sneak up on the derivative, the instantaneous rate of change, by finding the average rate of change for smaller and smaller changes. And how do we get the average rate of change? Well, we first find the change itself, and after finding the change, we get the average rate of change by dividing the change in the value of f by the change in x, and we take the limit as delta x approaches 0. And that's all that this says here. That's exactly what the definition of the derivative is. The first step is we get the change of f in terms of the change in x. That's what this says. Here's the old value of f, the value when x hasn't changed. Here's the value of f when x has changed. The difference between those two is the change in the value of f. Then the second step is we get the average rate of change by comparing the change in f to the change in x. That is, we divide. And then finally, we do this for smaller and smaller delta x's. Officially, we take the limit as delta x approaches 0. Okay, so that's what the derivative is. That's why the definition of the derivative looks like that. Let's apply it in this case. The function we have here is x cubed, so that says whatever you stick into f, you cube it. Here it is, x plus delta x, whole thing cubed. Now how do you multiply this out? How do you actually expand x plus delta x cubed? It's not just x cubed plus delta x cubed, right? There's a lot more to it. Let's take that on the side. X plus delta x cubed, that means multiply x plus delta x by itself 3 times. Look, I don't want to go through this too slowly, but you know how to multiply two things like this. You have two terms each, so you have to do something like, some people like to call it the FOIL method, the first terms, the outer terms, the inner terms, the last terms. The basic idea is each one of these has to multiply each one of these. It turns out that the inner ones and the outer ones are both x times delta x, so you get 2x delta x. Now, how do you handle this one? You can't use the FOIL method. You have to multiply each of these 3 by each of those 2. So x squared times x squared times delta x, this middle one times each of those, so on. I'm doing this really quickly. If you need to pause the video to see how it works out, please do so and work it out. You can all do this. Notice here that some of these terms are the same, so we combine them and we finally get this. This is x plus delta x cubed. That's what we wind up with. And we want to stick that in here, so let's move it up. It's just this, so we're going to replace that. We still have the limit as delta x approaches 0. We have all the other stuff. That's what we get. That's just a bunch of algebra. And now notice that x cubed is here, minus x cubed is here. We're going to actually subtract those so you get 0. And that's important because we want to ultimately divide by delta x. We can't yet divide by delta x because some of the terms don't have it. But once we subtract those two, one from the other, now every term has a delta x in it, top and bottom. We could divide top and bottom by delta x, and we wind up with this, right? The delta x over delta x, you just left 3x squared, delta x squared over delta x, we're left with a delta x cubed over delta x, that's a delta x squared. Now why is this important? Look back here, as delta x approaches 0, it's not obvious what happens. As delta x approaches 0, this one approaches this one, so it looks like it's approaching 0 on the top, 0 on the bottom. We don't know where that goes. But now we know, now we can see very clearly. As delta x approaches 0, 3x squared is not affected. 3x squared just stays the same. But these two, they have a delta x in them, so as delta x approaches 0, these two approach 0, so this is our limit, and of course, adding the zeros amounts to just making this 3x squared. That's the answer. We knew that was the answer. So this is kind of the standard proof. But what I want to show you is how does that relate to that proof we did with the cube? How does it relate to the discovery method, where we looked at the instantaneous rate of change of the volume of a cube? So let's really quickly run through that again. I'm going to do this really fast. Presumably you've just watched a video about discovering the derivative of x cubed by considering a cube, but here's what we did. We started with a cube of side x, and the reason we did that is because we wanted a physical expression of x cubed. The volume of a cube is exactly x cubed. So the question of the derivative is, how fast does the volume of a cube change when you change the side by a little bit? So if we change the side by a little bit, we grow it a little bit, we get a slightly bigger cube. It's bigger in 3 directions, coming out towards you, going to the right and going up. It's a slightly bigger cube. And the question is, how big is that volume? Well, we found it convenient to break that volume up into 3 pieces, right? Making the side a little bigger adds 3 slabs to the faces, and we saw that that was most of the volume, but there's a little more. There's the edges filled in, and finally there's the corner. And what we said to ourselves was, really, those edges and corner, they don't amount to much. As delta x approaches 0, these guys still have 2 dimensions of delta x. Rather, they have 2 dimensions of delta x. So when we get the average rate of change and we divide by delta x, they're still going to have delta x in them. They're going to shrink down to nothing. This is what really matters. And we see here the derivative is 3 because there's 3 faces times x squared. Now, let's just run through that again and see how that relates to the proof. This proof. We start with the cube. We make it a little bigger. That's exactly what this says. Look, this x plus delta x cubed, that's the volume of the bigger cube, the one that's outlined in purple. And we subtract off x cubed, that's the volume of the initial cube. So this top line here is simply the difference in the volume of the cubes, just like we said. Right? And how did we assess that? How did we analyze that change in volume? We broke it up into those 7 pieces I showed you before, but let's look at them again. 3 pieces like this, these big slabs on the faces. How big is each of these? X times delta x, and there are 3 of them. That's exactly that. 3x squared times delta x. That's the volume of the 3 faces. And then we looked at the 3 edges. How big are each of them? They have a dimension delta x, and a whole x. So it's 3 times delta x squared. It's exactly that. That's where that comes, and you can see what's going to happen here. The corner has dimensions delta x cubed. It's exactly that. So we see that this algebraic proof really corresponds exactly to the geometric proof. The 3 terms up here correspond to the 7 pieces that we used in our geometric proof. And not only that, but we said in the end that really the bulk of it comes from the 3 faces. As delta x approaches 0, the ratio of the volumes of these 7 pieces to delta x, really, it's all encapsulated here. The others go to 0. That's exactly what the algebraic proof shows you too. Right? The 3x squared came from here. The other parts, the edges and the corner, they both go to 0. So we see that the standard proof, the algebraic proof, which kind of leaves you feeling like, I'm not sure how it worked out that way, but great, it worked out that way, corresponds exactly to the geometric proof.